So let me jump into the lecture. What I want to do is I want to emphasize what sections of this chapter you don't need to read because it won't be on the exam. And so for the thermoeconomics, that whole section is don't need to read because it's not going to be on the exam. And matching end use to source is interesting reading, but not on the exam. The rest of it is pretty much on the exam. Okay, so all of this is that you're responsible for. Especially, we have a closed system exergy balance, and then we have the open system or control volume exergy rate balance. Only for steady state. We don't do transient control volume analysis. So this is where we have a the exergy rate balance equation. So it's a per kilowatt. Every unit is kilowatts, and it's for an open system of control volume. We only deal with steady state. And if you have just one heat transfer, then you don't have a summation in front of this term. You just have one Q dot multiplying by what's in parentheses. It looks like a Carnot efficiency. That's a good way of looking at it. 1 minus T naught over TB, such that this is less than 100%, meaning energy is being transferred in, but only a fraction of it is associated with the ability to do useful work. So the exergy transfer rate's less than the heat transfer rate by this fraction. We also have work out, and so it's an out with a negative, and that shaft work or electrical work is already in the form that we desire. It's in, so it's 100%, 1-to-1. There's no fraction reducing it right here. So if it's 5 kilowatts of shaft power out, it's 5 kilowatts of exergy transfer out. We also have for steady state one inlet and one outlet. So you just have one mass flow rate through the control volume. It brings in a flow exergy and goes out with either a higher or lower flow exergy. If the control volume is producing work, maybe it's a turbine, the in is high and the out is low. Out at state 2, the flow exergy will be lower. If it's a compressor, then this is a negative entity, not a positive entity. The power is going into the compressor, and the flow exergy increases. The flow exergy increases. We also have an out or a loss of exergy because it can be destroyed. Here is the difference in the flow exergies. Difference in enthalpy, that looks very familiar, minus T naught difference in entropy. So this accounts for not just the total energy, but it's the useful energy component. It's exergy. That's the concept of exergy. So the last section we need to deal with are taking a look at the turbine and common components and looking at a exergy balance equation for it, and then identifying what we call the second law efficiency or exergetic efficiency. So here goes. I have a turbine, and you can introduce a control volume around that turbine. So we have mass flow rate coming in and going out, and it's just one inlet, one outlet, steady state, so m dot's through the system. It brings in its flow exergy and goes out with the flow exergy. Well, if it's a turbine, which one is larger? The flow exergy in is larger, isn't it? Because it's producing useful work. So some of that exergy is coming out of the fluid stream and is going into the work. This power out. All right. So let's do an exergy balance for our system. We can write it down where it's steady state. There's 1 minus T naught over TB times Q dot, but there's no heat transfer for the turbine. Our most common assumption when you analyze a turbine is it's insulated. There's no heat transfer to the surroundings, so Q dot's 0. Then we'll have minus W dot. That's the same right here. Then we'll have m dot times EF1 minus EF2, change in the flow exergy from inlet to outlet, minus the exergy destruction rate. Did I write that equation correctly? Look good? Okay. What we want to do is that we want to think about interpreting this equation. So what I'll do is I'll write this. M dot EF1 minus EF2 is equal to W dot plus E dot D. Okay, there's a little bit of algebra, but I swapped some terms. I want you to look. Did I do the algebra correct from those two equations? Look good? Thumbs up? I see a couple head nods, but can you give me a thumbs up if you agree? Okay, good. So what it is we can interpret this. This is the exergy that's coming into the control volume, and it's coming into the control volume from the fluid stream. The fluid stream. It's coming out of the fluid stream. Where is that exergy going? It's going two places. One, it's going out of the control volume with the shaft work or the shaft power. And where else is it going out or away? It's being destroyed. See? It's being destroyed. True? So you can interpret this as so many kilowatts. Let's say I had 50 kilowatts coming out of the fluid stream, and maybe 30 kilowatts went into shaft power, and you know that then 20 kilowatts had to be destroyed. True? Now the goal would be to minimize this destruction. Don't we want to minimize? It's just wasted potential to do useful work. You didn't destroy energy, you destroyed the ability to do useful work if you have exergy destruction. So they say, look, now that we have this concept of both the first law and the second law coming into play, why don't we have an exergetic efficiency? The book uses a symbol epsilon for the exergetic efficiency, and it'll be the ratio of something that you want to have a lot of divided by what you had to pay for. What you want over what it cost. That's a good ratio for efficiency. So what did we want? We wanted a lot of power out of this turbine. What did we have to pay for? Well, it comes at the expense. It doesn't run, it doesn't work unless there's a change in the exergy coming out of that fluid stream. And so now you can see that what does epsilon do? How can it get to 100%? By having exergy destruction go to zero. True? That's how you do it. And as exergy destruction increases, the exergetic efficiency, also known as the second law efficiency for the turbine, goes down. Let's solve this problem. So we have water at 8 megapascals and 20 degrees C enters an insulated hydraulic turbine. So what do they mean by hydraulic when you see the word hydraulic? There is no phase change. It's all liquid. It's a liquid turbine. It's not a steam turbine. It's a liquid water turbine. Where would you use or see a hydraulic turbine in practice? A big hydroelectric generating station, something like the, what is it, Hoover out in Boulder City? Hoover Dam, right. They have some really big hydraulic turbines there, been running for a long time. So the water goes through it. It comes in at really high pressure, 8 megapascal, that's just a number. And then it drops to 1 megapascal. It expands or drops pressure to 1 megapascal. Okay?
So when you say hydraulic again, you meant no phase change, right? It stays liquid.
Yeah, it stays liquid, all liquid. Mm-hmm. And so here, the effects of motion and gravity are neglected, and the dead state temperature and pressure are given. The first question of the 3 parts is, what is the work developed? So you can make an illustration of the turbine, kind of reproducing what we had on the other slide. Goes out at 1, in at 1, out at 2, and there's shaft power, the steady state, so 1 m dot through the system. And when you do an energy balance for the control volume around this turbine, just an energy, nothing to do with exergy yet. Part A is just energy balance. What do we find? We find that the in the mass flow rate times enthalpy 1 minus enthalpy 2 is equal to W dot. Do you agree? Thumbs up? Couple steps. You should go slowly as you study, but I only have a limited amount of space, and I need to go a little faster, okay? But you need to make sure that you agree. Start with the most general equation, conservation of energy, and manipulate each term. Now, it's an insulated turbine, so we know Q dot's equal to 0, etc. Or you have to say, oh, I'm going to make this assumption. So I have a table of properties. Here is the enthalpy state 1. Here is the enthalpy state 2. And so we can compute this W dot over M dot, also sometimes written as lowercase w specific work, is equal to just H1 minus H2, and you calculate lowercase w. The answer for part A comes in at a whopping 6.56 kilojoules per kilogram water going through the hydraulic turbine. Part B, what is the isentropic efficiency? This efficiency is what you were used to in the previous semester. You mastered the isentropic efficiency. Now, for part C, it's the exergetic efficiency. Okay, so in order to calculate the isentropic efficiency, you need to consider not just expansion from 1 to 2, but from 1 to 2s, where the pressure at state 2s is known and the entropy is known. True? So you conceptually calculate state 2s, and you find that this is state H2s. That's the enthalpy at state 2s. And so the work, assuming isentropic expansion, is not, it's going to be H1 minus H2s, is not 6.56 kilojoules per kilogram, but is actually 6.99 kilojoules per kilogram. So if you had completely reversible expansion from 8,000 to 1,000 kilopascal, you would get more work out per unit mass flow. So we calculate the turbine isentropic efficiency is the actual divided by the isentropic work. And so it's 6.56 divided by 6.99. You'd find it's 93.8%. That is an efficiency measure, which is a good efficiency measure for this turbine. And now we have a second efficiency measure known as the exergetic efficiency measure. Well, how do we calculate that? We could put epsilon T. The book usually doesn't put a T for turbine, but I like to put it on there. It's the second law efficiency for the turbine. It's equal to the work that you actually get out divided by the change in the flow exergies. Now, I computed these and put an extra column for the flow exergy because it's just another property, is it not? And this was computed in Excel. True? You could kind of see that. And all I did was for the flow exergy at state 1 was I said EF1 is equal to H1 minus H0, the dead state. Well, I ran first row is the dead state properties, so I had to get H0 right here and S0 right there. So H1 minus H0, so it's 91.42 minus this value for H0 minus T0. Well, for this problem, the dead state temperature is 25, or T0 is 298 Kelvin. So we put 298 there. S minus S0, and I neglect effects of motion and gravity, so kinetic and potential energy are negligible at state 1, 2s, and 2. And so that's how we calculate it. You use this value, this value, this value, this value, plus 298, boom. You have it. How many people have used Excel? At the end of the semester, all the hands will go up because you'll have to use it, and I'll show you how to use it for the problem, for the design projects. So, but don't, it's just a table to help organize information, and then you can use different values out of different cells, parts of the table, to make it automated so it's really easy to calculate something like this number right here, 8.0749. I didn't input by typing it in, I let it calculate it, right? And likewise, it calculated this one, it calculated that one. So we have now the difference in these flow exergies, 1 to 2, and when we calculate the second law efficiency, we get 93.6%. Which one's better? They're not any better. They're both different measures. One thing about the second law efficiency, though, is we can do it for a heat exchanger. Did we have an isentropic efficiency for a heat exchanger in Thermo 1? No. Also, if you go back and you say, I have a Carnot heat engine, true? And I'm bringing in heat from a high temperature QH, and I'm rejecting some heat at a QC. And then you ask yourself, what is the thermal efficiency of that Carnot heat engine? And you come up with about 43% or something. And then you report it. And you know, every now and then you'll hear this out in the news. They'll say, these engineers are so either stupid that the maximum efficiency they can get out of a power plant is like 43%. Well, theoretically, the Carnot, with that high temperature here and that low temperature here, it may be limited to be 43%. But it doesn't sound good. It's like, you know, go out there, team, and give it your 43%. Come on now, let's win this game. No, the coach always says 110%, but engineers, we can't lie. So what we do is if you measure, basically, if you compute the second law efficiency for a heat engine, and it's operating at the upper limit, no entropy generation, no exergy destruction, you'll be to 100%. You've renormalized your scale. Okay. So, but this is not flawed. Neither of these are flawed, and neither of them are have some super advantage over the other, but there are some advantages for a second law efficiency, and I tried to point that out. Let's continue. Let's work it out for a compressor. The only reason to do this for a compressor or a pump is because this W dot's going to be negative by definition, true? But we'll leave it as going to be negative. And you go in here and you do a control volume analysis, and you write the Exergy balance equation, and it's not going to look any different than what we just had for our turbine. Minus W dot plus M dot EF1 minus EF2 minus Exergy destruction rate. True? But I'm going to ask a question. EF2, is it equal to EF1? Is it greater than EF1 or less than EF1 for the compressor? EF2 will be greater than EF1. True? What you're doing is you're putting energy into the fluid stream with the pump or compressor. Good. So what we want to do is rearrange this equation. So let me rearrange it. M dot EF2 minus EF1 equal to positive W dot, no, not positive W dot, negative W dot. And let me do this. I got to switch that to this side. Minus E dot D. No, that's not what I wanted to write. I'm sorry. I have to rewrite this. I wanted to write it this way. W dot's equal to, okay, we put that over there, minus M dot EF1 minus EF2 minus E dot D. Did I write that correctly?
I think you don't need the minus in front of it. M dot EF1.
That's right. That's right. So, oh yeah, that's what I wanted to do. I wanted to put 2 here, 1 there with a minus sign. Is that true? Now put the minus sign over here, get rid of all these minus signs. Now I finally got it to the form I wanted. Sorry. Okay, why? It's just algebra, but what is this term? As an entity with the, see, W dot's negative, you put a negative in front of it, it's positive. So this is a positive inflow of exergy with the work, right?
Why is ED still positive?
It's positive.
Shouldn't that say negative?
No, I don't think so. Let me ask everybody, check my algebra right now, and if you agree, give me a thumbs up, and if not, give me a thumbs down. It takes you saw me stumble. It takes a little bit, but I want to conserve space. This equation here is correct, and all I have to do is get to that one. So maybe I do this. Conceptually multiply everything by a negative, and then bring it to the other side. Bring W to the other side. Maybe that was the easier way to visualize it. Thank you for your thumbs up. So this is a positive amount, and it's the flow of exergy into the system, inflow. And where does it go? It goes into the fluid stream, or where does it go? Destroyed. Which one do we like? We like to get it into the fluid stream. Which do we not like? Destruction. So you could see this is a good definition of the exergy for a pump or compressor. What do we want? We want m dot over EF2 minus EF1 to be large compared to minus W dot. And that's exactly the same equation developed in the textbook, and I wanted to be consistent with the textbook, okay? So otherwise I was very tempted to turn this around and let that be a positive W dot in, but that would be inconsistent. So, you see that? All right. Well, you can also do a second law efficiency for a heat exchanger. Here's the heat exchanger where you have a hot fluid stream going on one side and a cold fluid stream going on the other side, and they don't mix. True? They do not mix. So we have no mixing. Do we have heat transfer this way inside the heat exchanger? But the heat exchanger is, they call it an adiabatic heat exchanger. The first time you hear that, you think, what? Adiabatic means no heat transfer. Heat exchanger, that sounds like a dud. But it's no heat transfer with the surroundings. Heat transfers inside, but not to the surroundings of the heat exchanger. So we want to identify a second law efficiency for this heat exchanger. First of all, do a control volume and do an exergy balance. So if we do an exergy balance, we have steady state. There's no Q dot, so I'm going to put a 0 there. There's no shaft work, so I'm going to put a -0 there for the kind of visualize. No Q dot with the surroundings. No W dot with the surroundings. And then we're going to have a mass flow rate of the hot fluid coming in, and it brings with it its flow exergy at 1. Oh, it also takes out the flow exergy at 2. Plus the mass flow rate of cold fluid coming in at 3, going out at 4, minus any destruction of exergy which happens within that heat exchanger, within that control volume. Does that exergy balance equation look good? We have two fluid streams, both have inlet, outlet, right? So it looks a little complicated. Let's rewrite this equation, or first of all, let me do this one. EF2, is it greater than EF1 or less than EF1? The flow exergy coming out at 2. I have a less than. I have a less than. It's less than, isn't it? You think about a hot fluid stream. It has a lot of potential to make work, useful work. Let's say I have a lukewarm fluid stream. I have less potential to do work, true? And so EF, the flow exergy, is the measure of how is it ready to make some useful work, okay? And so it's, as it goes through the hot side, it goes through. Is it going to be, here's an easier one, T2 compared to T1. The temperature, what do you think? hot fluid got hotter, or did the hot fluid become warm? It became warm. So the temperature went down. Likewise, the flow exergy went down. So what we do is switch this other m dot h, EF1 minus EF2. Put that onto the left-hand side. Now, how about the flow exergy at 3 and the flow exergy at 4? 4 is the outlet of the cold fluid, right? How does the flow exergy at 4 compare to the flow exergy at 3 for the cold fluid? Did EF4 go up? Is it greater than EF3? Yes, it is. True? True. The cold fluid became warm, if you want to think of it that way. All right. So that's equal to m dot C EF3 minus EF4. This is a positive difference. This is a positive difference. I'm trying to just write things in positive. Let me finish this off. And then we have a minus exergy destruction rate. Whoops, why do I write a minus there? That's right. Okay. Why is that a plus? I messed up somehow.
You didn't swap your E's.
Oh. So this is 4, 3 and positive. Okay. That's right. I did it right. Now stop and check me for a sign error, because I did have one a second ago. Is that what you were raising your hand about?
I don't understand how moving those things around affects the ET, why it goes from negative to positive. I'm looking at it algebraically and it doesn't make sense.
Okay, well, as it's written, this is positive as written. This is negative, and this definitely has a negative sign in front of it. So what I want to do is put something on the left-hand side, which is simply positive. Then I can interpret this. This is the contribution of flow exergy from the hot stream. That's what really drives the heat exchanger, if you want to think of it that way. It drives the heat exchanger. So this is into the heat exchanger, where it's from the hot fluid stream. I'm trying to build up so I can interpret this.
I think I got it.
Okay.
The MC.
I know.
Yeah, but I get it now.
Yeah. So I wanted to kind of read it from left to right. That's why a lot of extra. Now what we have is it goes into this is now coming out of the heat exchanger. It's coming. It went into the cold fluid. It went into the cold fluid stream. And what is this? Well, this is our destruction. Do we like a lot of destruction of exergy? No. We don't like that. The best would be zero destruction of exergy. All the exergy came out of the hot 100% right into the cold, but that's not going to happen. So we have a measure of the performance, the second law efficiency, or the exergetic efficiency of our heat exchanger, which is what do we really want? That's kind of on the right-hand side without the destruction. We want it to get into the cold fluid. And what do we have to pay for? What drives it? What makes it work? Coming out of the hot fluid. EF1 minus EF2. So there's a measure of the exergetic efficiency for this heat exchanger. We call it a counterflow heat exchanger, but it's a non-mixing heat exchanger. Do we have a comparable efficiency from entropy? No, we don't. So this is nice. This is a little benefit, where we now have an efficiency for a heat exchanger. Thumbs up, ready to go? Let's go to the next one. Now we have a heat exchanger, but this one is called a direct contact heat exchanger. Think about it. I bring in a hot fluid, it goes from 1. I bring in a cold fluid, it's coming from 2. And we only have one outlet, that's 3. So the cold and the hot mix to create something that's lukewarm. And this happens a lot in power plants and other devices. So we have the mass flow rate at 1 coming in, 2 coming in, 3 going out. The flow exergy in at 1, flow exergy in at 2, and the flow exergy out at 3. Let's go ahead and write an exergy. Well, do this first. Do a mass balance. I know it's simple, but what does the mass balance equation give you? The sum of the ins has to equal the sum of the outs. There's only one out. So anytime I see m.3, I can replace it with m.1 plus m.2. That's the utility or usefulness of this mass balance. If you wanted to, you could do an energy balance. Just let's do the energy balance. You're going to find H1 m.1, or put m dot before the H, it really doesn't matter. m.1 H1, bringing with it its enthalpy, plus m.2 H2 is equal to m.3 H3. Does that equation make sense? We want to be able to read our energy balance. Start with the most general energy balance equation, write it, apply it to this control volume, manipulate, take a couple lines, and get to that result. But hopefully that equation is readable. Now we want to write it for an exergy balance. For what? This control volume. Okay, so what we're going to have is there any Q dot? Nope. With the surroundings. So what we have is 0 is equal to 0 plus 0. We're going to have m.1 coming with its EF1 plus m.2 EF2 minus m.3 EF3. And do I put a minus E.D? Yes, we do. Stop, pause, did it look good? I have a plus in front of the in at 1, plus in front of the in at 2, a minus in front of the out at 3. That all look good? Good. Now, what I want to do is I want to substitute for this m.3 right there. What do I substitute? m.1 plus m.2. True? And then I want to rearrange it, and I know I'm going to try and do it quickly here. But it's going to be m.1 times EF1 minus EF3 is equal to m.2 times EF3 minus EF2 plus E.D. I'm going to pause. And I want you to look at that algebra and give me a thumbs up if you agree and a thumbs down if I made a mistake. I got a lot of thumbs up. Any thumbs down? I know I did it a couple ways, but I like to read from left to right. So what do we interpret this as coming in right here? The hot stream, think about, maybe I draw it like this. The hot stream comes and goes like that. The cold stream comes and goes like that. And they're joined together at the outlet. And really what's happening is there's a transfer from the hot to the cold to get them lukewarm. We're in between, true? So what really is driving this thing or making it work is what comes out of the hot stream. Where does the exergy go that comes out of the hot stream? It goes, guess where? Where? Into the cold. This is called cold. I know it's cold to lukewarm, hot to lukewarm, but it goes into the cold stream, true? And, or it gets destroyed. Now, can you give me a good exergetic efficiency for this direct contact heat exchanger? What do we really want? What do we really want? And what do we have to pay for? What drives the thing? What is the expense? The expense is coming out of the hot stream. True? And what do we want? We don't want destruction. We want as much of that to get into the cold stream. I pause. I let you digest. Does it look good? Good? You ready to apply it to a problem? Let's solve a problem. So we have an insulated direct contact heat exchanger operating at steady state with water entering as a saturated vapor. So let me try and draw it up here. We'll have inlet 1, and this is water as saturated vapor. Okay, it comes in at 1 bar. And we could look up the temperature, which is T1, this is P1. It's Psat at 1 bar, which is just under 100 degrees C, 99 something. Let me look at my notes. It's around 99 degrees C. Okay? 99.6 degrees C, the saturation temperature for water at 1 bar. And then it has a flow rate, M.1, of 5 kilograms per second. Now it mixes with state 2. M.2 is 3 kilograms per second. Now, it is liquid water. We don't want to mix CO2 and water. We don't want to mix refrigerant and oil. You just have water mix, okay? So the water's coming in at T2 of 25 degrees C and 1 bar. Okay? And what do you think about the condition of water at 25 degrees C, 1 bar? Superheated vapor? Subcooled liquid? Two-phase liquid vapor? Well, this is the saturation temperature at 1 bar. Subcooled. It's liquid. It's just liquid water. So we have this saturated vapor mixing with liquid water that's cold. It's subcooled liquid. And what's going to come out is state 3, and it's definitely water. Okay. There's negligible pressure drop in the heat exchanger. So we know that everything is 1 bar coming out, going in. So no pressure changes. And neglect effects of motion and gravity, so kinetic potential energy effects are negligible. Dead state temperature and pressure, common. Determine the exit temperature of the water. Nothing to do with thermo 2, it's just thermo 1. Can I get the exit temperature of the water? Can I find T3? True? Isn't that what we're asked to find? So we'll do a control volume analysis about that direct contact heat exchanger, and we'll write down the energy balance, and I wrote it down the previous slide. M.1 H1 plus M.2 H2 is equal to M.3 H3. A lot of times I like to check. It's like, do I know M.1 from the information given? Yeah. M.2 from the information given. Can I calculate, or do I know M.3 from the information given? Well, you do a mass balance and you sum this and this, and so you find that M.3 from a mass balance is 8 kilograms per second. True? So I got M.3. How about H1? Can I get H1? That's H of G at 1 bar. True? So I can get that one. How about H2? H2. Oh, it's subcooled liquid, water, 25 degrees C. You can get it. I think we can. How would we get it? H2 is equal to H of F at 25 degrees C. That's a great approximation. True? So we can get H2. The only thing unknown in this equation, this energy balance equation, is H3. So I actually calculate H3, and now I know the pressure. So I compare H3 with H of F and H of G, and I see it's in between. What does that mean about the state 3? I have a quality. It's a two-phase mixture. I had saturated vapor. I brought in some cold liquid, and now I have some two-phase mixture at 1 bar going out, right? And when we do that, we find that the quality at 3 is H3 minus H of F divided by Hg minus H of F. And you can calculate it's around 57.3%. So it's a two-phase mixture. Okay? It condensed some of that saturated vapor that cold liquid did. All right. So what is the temperature of the water coming out? It's a saturation temperature at 1 bar. So is the temperature at 3 equal to 99.6 degrees C? That seems funny, doesn't it? 99.6 degrees C, something coming in, 20 degrees C coming in, and I still get 99.6 going out. All I did was condense some of that saturated vapor in stream 1. Now, what is the rate of exergy destruction in units of kilowatts? How would we find that? Two strategies. First strategy is you can say that the rate of exergy destruction is equal to T naught times the rate of entropy production, and go and get the rate of entropy production. You can do that way. You can also do an exergy balance where you say the mass flow rate at 1, EF1 minus EF3, that's what comes out of that hot stream, goes to M dot 2, EF3 minus EF2, that's what's going into the cold stream, plus some destruction, true? And you can calculate this first term, the second term, and the exergy destruction. Either way, let me give you some numbers because I see I'm running a little bit out of time. The exergy destruction rate is going to be 86.7 kilowatts. All right. That comes out of the hot fluid is 699.4 kilowatts. What goes into the other fluid stream is 879.7 kilowatts, meaning 86.7 kilowatts. Something looks, no, that's right. Okay. So now the last, so that's part B. There's answer to part A, answer to part B. Now, what's the exergetic efficiency of that heat exchanger? You can calculate it two ways. You could say the exergetic efficiency is what I really wanted, that's the 879.7 kilowatts going into the cold fluid stream, over 699.4 kilowatts coming out of the hot fluid stream, and you calculate that it's 91.0%. True? There's one other way to calculate the exergetic efficiency, and it uses the exergy destruction, but just calculate it this one way is good. All right, we got 4 minutes. Does anybody have a comment or question? Yes, sir.
So you're saying 87 divided by 69?
Oh boy, I put them in wrong, didn't I? Thank you. It's the 879.7 divided by, oh man, I wrote that number wrong. 966.4 kilowatts. 966.4 kilowatts. Thank you. Sorry, just trying to go too fast. Any other comments or questions? Thank you for your attention. We'll see you later.